start. So welcome everybody. Today we are really happy to have Venkatesan Guruswami from CMU to tell us about Boolean CSPs and how to refute them.
Right. Thanks, Savi, for the invitation, and thanks to all of you for tuning in. Yeah, so I'll be talking about refuting constraint satisfaction problems, which are oh, by the way, Avi, should we record this? Or, I mean, there was some question.
It's being recorded. It's all
okay.
the seminars are recorded unless you have an objection.
Okay, no, because they said that somebody will explicitly ask me and I should give an okay. So I just wanted to check.
Yeah, you are very good. Most people don't. But anyway, yeah, it is recorded. I can see it.
Excellent.
Yeah.
Okay, so I'll be talking about refuting semi-random Boolean constraint satisfaction problems, and this is joint work with Jackson Abascal, who's a PhD student at CMU, and my colleague Pravesh Kothari. Okay, so I'll start with defining this Boolean KXR problem, which is a fundamental CSP or constraint satisfaction problem. So here you have n variables, which should take Boolean values 0, 1, and you have a collection of equations mod 2 on constraining those variables, where each variable stipulates that the parity of k of those variables is either 1 or 0. So for example, you might have k equals 3 and you have Boolean 3 XOR. So you have a collection of equations like this on 3 variables, and the right-hand sides being 1 or 0. And of course, this being a linear system, it is very easy to ascertain satisfiability. But the question we'll be interested in is the optimization question. How many equations can you simultaneously satisfy? And of course, for this problem, there is a very seminal and very strong hardness result due to Hostad, which says that even if the instance is almost satisfiable, you can't do better than just random guessing. So, and this is true for every k at least 3. Even if most equations are satisfiable, you can't get more than 50% of them satisfied in any single assignment. Okay, so and this talk is going to be about an average case and well-studied variant of KXR.
Okay. Venkat, can you go back to the previous slide?
Sure.
Yeah, I just think, for some people in the audience may not have seen this result, the Hostad result, and I think it just maybe is worth stressing or repeating because everybody thinks that, solving linear equations are difficult, that, if you have a system of linear equations mod 2, to satisfy half of them is easy simply by tossing coins for the variables. And what this says is that even if almost all or 99% are satisfiable by some assignment, it's NP hard to satisfy more than 51%. So it's, to me, one of the most stunning hardness of approximation results.
Yeah, so thanks, Avi. Yeah, I think I should have mentioned where this half comes from. The half is in some sense trivial because you can just either set a random assignment, or in the case of odd things, you can set all of them to be 0 or all of them to be 1, and one of them will get at least half. So either of these trivial algorithm works, and Hostad's result says that this is basically the best you can do. It somehow says that Gaussian elimination is extremely sensitive to noise. So even if you have a tiny amount of noise, we really have no good algorithms. Okay, so we will now consider not worst case problems, but random problems. So here again, we will be given m equations, each having k variables and constraining n variables, and you'll have some right-hand sides. But now I'll pick the right-hand sides completely at random. And the semi-random model, as opposed to the random model, is when the matrix A or the equations are arbitrary. It's only the right-hand side which is random. Okay, so in this case, just using standard Chernoff and union bound arguments, you can show that if you sample enough equations, but if you set their right-hand sides completely at random, then there will be no assignment which gets more than half plus epsilon of the equations correct. Okay, so this is just standard concentration bounds, and this probability being taken over the random choice of R. But now the algorithmic question becomes, can you somehow certify this? So given this random instance, can you somehow prove efficiently that you cannot satisfy too many constraints? And the question is, this becomes easier as the number of constraints becomes more and more. So you would like to understand at what number of constraints, this parameter m, can you give an efficient upper bound on the opt? Well, opt I'll use to denote the largest fraction of equations you can simultaneously satisfy. Okay, so and I'll be a little bit more formal on this in the next slide. So I want to state our result right away. So what we do in this work is that for KXR, we give a strong refutation in the semi-random model as soon as the number of equations is about n to the k over 2. And this funny O tilde indicates that I'm hiding some polylog factors. So think of this as n to the k over 2 times some log square n or something. And contrast this with the fact that information theoretically, we only need a linear number of equations like order n, but here we're using a lot more. But the thing is, we will give an efficient algorithmic proof. And you have to be slightly careful what an algorithm refutation means. So what we can do is that for any k greater or equal to 2, we can give an efficient algorithm, which on a KXR semi-random KXR instance will output an answer alg of the instance, such that will always, for all instances, be a valid upper bound. So if I say 0.9, then I'm absolutely sure that the instance, you cannot satisfy more than 90% of the equation. So that is with certainty. But of course, if you just want the first property, it's trivial. I can always output 1 because you cannot satisfy more than all the constraints. So the usefulness comes from the second part, which says that if there are enough constraints, and here I just wrote down this in full detail, but roughly n to the k over 2, then my upper bound will be really good. My upper bound will be very close to half with overwhelming probability. Okay, with probability, let's say 0.99. So this is our main result. And this also implies using known reductions, similar results for all semi-random, all constraint satisfaction problems. And basically what it does is that it does what we could do in a fully random model in the semi-random model up to some polylog factors. Okay, and I'll say more about these things shortly. And previously, this was known in the sense, in two senses. One is that if the equations were completely random, we had a similar result to our main result. And we also had the same result even in the semi-random model when k was even. Somehow the case of even k is much easier than the odd k here. So you should think of 3XOR as a particularly pesky problem in this model. Okay, so hopefully the main result is clear, and I'll come back to recapping the main result after telling you a bit more about random constraint satisfaction problems. So this is the picture of the talk. So I'll spend a reasonable amount of time on the history of the problem, even though I'll be abridged. I want to give some context for this work. And then I'll talk about the even k case, which is quite simple. And then we'll move towards odd k, where I'll really focus on 3XOR, which indicates all the ideas. Okay, and then there again, we'll talk about the random case first. And then finally, just I'll have a little bit of time to just say the semi-random case, which is our main new part. Okay, so most of the talk will be really the background and prior works leading up to this. And towards the end, I'll say what's new and what we are doing. And there are many open questions. I hope to highlight some of them at the end. Okay, so first I want to give some broader context of random Boolean constraint satisfaction problems. So here the model is, so we talked about the XR problem, but in general, you can have any Boolean predicate, which is given by P. And for convenience, we'll indicate the domain by +1, -1 rather than 0, 1. And how do you sample a CSP instance, or what is a CSP instance, CSPP instance? You have n variables, x1 through xn, and you're going to have a collection of constraints. So each constraint is specified by a tuple of k distinct variables, as well as a negation pattern. So you say which variable appears negated and which one doesn't appear negated. And then the constraint is, and these I just think of as signs. And now the constraint simply says that P on those variables with that negation pattern applied should be 1. So this is what a CSP looks like. For example, you might have P to be the OR predicate. One of them is true, and then you'll get the KSAT problem, because you will take k variables and you will say at least one of them is true. Well, you can also do negation. So you'll say either x1 is true or x2 is false or x4 is true. Okay, so things like that. And in the random CSP instance, so if P is going to be fixed in this problem, but to define the instance, I need to tell you the tuples and the negation patterns. In a random CSP, all the tuples as well as the negation patterns will be sampled uniformly and independently at random. So everything is random. So if you go back to the KXR thing, it will be the case that the scope of the equations is also random, in addition to the right-hand sides being random. Whereas in the semi-random model, it's only the equations, the equations can be arbitrary. So in particular, the tuples or the scope of the constraints can be arbitrary, but the negation patterns are applied uniformly at random. And if you think about it for the XR case, this is equivalent to saying that you have arbitrary equations, and you can take all the negations and move it to the right hand side as a random bit. Okay, yes, question?
So is it important here that you don't allow the same variable and its negation in a tuple?
Yeah, let's say that the variables are all distinct. Yeah, so you can consider some other models, but for simplicity, and it's cleanest if you just allow distinct variables.
Okay.
So it's actually a tuple of k distinct variables.
Okay.
And of course, if you sample things randomly, that will happen with high probability anyway. But let's just keep that model. Yeah. So it's k distinct variables. Okay. And of course, in either case, whether it is random or semi-random, if you sample enough constraints, where enough is basically something like n over epsilon square, then your opt will not be large. Well, I said it's at most half plus epsilon in the KXR case. For an arbitrary predicate, it will be a fraction. You will take the fraction of assignments which make P1 and plus epsilon. Because if you just give a random assignment, each of these constraints will be satisfied with exactly this probability indicated here. So if you give me an epsilon extra, you will not be able to satisfy that. Okay, so this is just standard concentration bounds. Okay, so we know that the optimum is very large, and we want a refutation algorithm for this. And note that the refutation algorithm should always be a valid upper bound on the optimum. So now the challenge is, what is the smallest number of constraints for which we can do this efficient refutation? Okay, and the refutation can mean multiple things. So there are a weak refutation will simply be something where the algorithm outputs something less than 1, which means you have at least proven that the instance is not satisfiable completely. Okay, for many things like CNF satisfiability, this is very important and well studied. So that's weak refutation. You're simply saying you can't satisfy everything completely. Of course, for KXR, this is trivial because Gaussian elimination will allow you to do this. But for other predicates, this is already non-trivial. You can also ask for strong refutation, which means that you prove that the fraction of satisfiable constraints is bounded away from 1 by a quantity which can sort of depend on the predicate. Let's say you prove it's at most 0.99. Okay, that is definitely stronger than weak refutation. And then you can have ultra strong refutation. Again, this weak and strong are standard terminology. I think the ultra strong I just made up, but that just says that you cannot do better than random. So you're really close to what the true optimum is. Okay, so those are 3 forms of refutation. And obviously we would like to get ultra strong refutation if we can. And it turns out things like KXR, it's important. Even if you only want weak refutation for some other predicate, getting it strong for XOR is important. So that's what we'll focus on. Okay, so it's a little bit of this problem has a very rich history, but I'll just give some snippets which are sort of most relevant to this work. And so it's studied in multiple facets. First of all, it's very important in probability. You want to understand things like satisfiability threshold. There's huge amounts of work there. But our focus is more the algorithmic aspects, and there too, there has been a lot of work. And in the complexity aspect, it was first studied in proof complexity, where people wanted to understand, okay, how basically these were giving hard instances for resolution proofs, and that was studied in the 80s and 90s in these works. And then sort of in 2000s, the focus shifted from combinatorial refutations to spectral refutations. And so work by Friedman, Gert, and Gert-Krivilevich basically allowed spectral refutations, which basically kind of for KSAT, where the predicate is the OR predicate, got to bounds which are roughly similar to what we are getting, but not quite, because this is a seal of K over 2 rather than K over 2. Okay, and in 2002, there was a very important and influential work by Feige, who instead of just talking about weak refutation, said that even strong refutation, so he basically said that, okay, what about strong refutation? And he made an assumption that you cannot do strong refutation if you don't have too many clauses. And this, in a way, was a weaker assumption, because you are only ruling out strong refutation. And so there was confidence in this hypothesis, which he called the random 3-SAT hypothesis for 3-SAT. And this was very influential. It triggered many results in inapproximability, learning theory, cryptography, and so on. And then there were follow-up works by Koja, Oglan, and others who said strong refutation, who gave strong refutation algorithms with good class densities for 3-SAT and 4-SAT. And I also want to mention this one sort of very cool work by Feige Kim Ofek, which also talked about non-deterministic refutations, where he said, I don't have to give an efficient algorithm, but I'll give you a short proof of unsatisfiability. And there, surprisingly, they showed you can go below this n to the 3/2 bound for 3-sat, okay, which still stands as the best that result. Okay, this is all for KSAT. But going beyond KSAT, now we are interested in an arbitrary CSP based on a Boolean predicate P. So an interesting question is, how does the predicate itself affect the number of constraints you need for refutation? Okay, and it turns out this was also studied sporadically initially. Well, people noticed that for certain predicates like not all equal 3-sat, or if you want to say that exactly half the literal should be true, then you can actually refute with a linear number of constraints. Works in the early 2000s. And another very influential work was by Goldreich, who said that he basically gave candidate one-way functions based on random instances of CSPP. And he said that, if you believe these things are hard, you get one-way functions. And later people also postulated these were pseudo-random generators. And this was also more systematically investigated in work by Applebaum, Barak, and Avi, who gave public key crypto primitives as well. So there was a beautiful connection between assuming that refutation is hard and basically putting it to work for getting efficient cryptographic primitives, which were somehow very different than traditional way of doing things, and also has relevance in the post-quantum world, because a lot of these problems don't have good quantum algorithms as well. So these interactability hypotheses you might as well make against quantum algorithms too, if you want. And another beautiful work was by Daniele Linial and Shalev Schwartz, who said, if you assume certain refutation problems are hard, then you can actually show that certain improper learning theory tasks are hard. And again, this seemed kind of quite beyond what we could prove using other methods. And this was a beautiful connection between constraint satisfaction and interactability of learning. And actually, this triggered a work by Allen, O'Donnell, and Whitmer, who probably for the first time initiated a systematic study of how does the predicate affect the refutation threshold. And so they, and we will mention their work many times in this talk, but they studied completely the random case. And you could effectively say we are doing what they did for the random case in the semi-random model. And one of their motivations was this work of Daniele and others on the hardness of learning. And indeed, they were able to refute some of the hypotheses they made. But many other hypotheses stood, and this is still a very interesting connection between CSPs and learning. Okay, so this slide just to show that this is seems like a very specific problem, but it has many broader connections to what we do across theoretical computer science. Okay, and so again, on the one hand, we want to study CSP for an arbitrary predicate. That seems like a lot of many different kinds of problems, but it turns out it's really only one CSP which matters, which is XOR, if you refute it properly. Okay, so this is sort of loosely called the XOR principle. It was implicitly there already in Feige's work and played an important role there. And it was really made explicit in this Allen O'Donnell Whitmer work. So basically it said that if you refute XOR in a strong enough way, if you give an ultra strong refutation of XOR predicate, linear equations, then essentially you can do the same for any predicate. Okay, so a bit more formally, what is shown is that if you have an arbitrary predicate P, you can refute random instances of it with a number of constraints, which is essentially the same as you need to strongly refute or ultra strongly refute T XOR, where T is some parameter of the predicate. Okay, so one thing you can certainly put T as is to be K, right? Because if K is the arity of the predicate, but it turns out for many predicates, you can actually do much smaller. And what is really important is not the arity of the predicate, but rather how uniform the predicate is. So if the predicate can support a distribution which is T-1 wise uniform, but not T wise uniform, then effectively it's really like a T XOR problem. So in particular, by our results, you can do it in n to the T/2 constraints. Okay, and T wise uniforms, T-1 uniform just means that if I take any T-1 of the variables inside the predicate satisfying assignment, they will be completely uniform. Okay, but on the other hand, if you take T of them, they won't be uniform. So if you take K sat, T equals K. Whereas because on any K minus 1 things, it can be uniform, but on K things, it cannot be uniform because you know that at least one of them has to be 1. Okay, so again, this is not so important for the talk, but this is just to say that there is a crisp and completely tight connection which allows you to move from an arbitrary predicate to XOR.
Venkat, one question.
Yeah.
So in the previous slide, the algorithms you mentioned for refuting certain CSPs with linearly many clauses, are those all predicates that are pairwise uniform?
Yeah, so those will be things which are not pairwise uniform.
So,
if you take not all equal 3 sort, yeah, they are not even pairwise uniform.
Yeah, okay.
Yeah, it's slightly confusing because I call T to be degree of uniformity. It's actually one more than that. Yeah, this is. So those are not pairwise independent, and so you can do it with linear number of constraints. Okay, and this parameter also occurs in, again, a different model, but somewhat related model to this, which I won't talk about here, is the planted model, where you actually plant a satisfying assignment and subject and sample constraints which respect that assignment. And that's also a very important model. And this parameter also occurs in that line of work of Feldman, Perkins, and Mempala, but the algorithms are rather different. Okay, but I'll only focus about refuting, where you sample enough constraints so you're sure there is no good assignment. You just have to prove. Okay, and it's really in this context that so it becomes, the whole game is about XOR, and and here it turns out, if you give me enough random KXR equations, an ultra strong refutation of it, proving that you can't satisfy more than half the equations, was achieved with the current state of the art number of constraints, which is basically n to the k over 2. Okay, and this was done in 2 works about 5 years ago, one by Barak and Moitra, 2 independent, more or less concurrent works, Barak, Moitra, as well as this AOW work, which I mentioned. Okay, and again, what we are doing is essentially amplifying this result to prove it in the semi-random case. And there is some, you might wonder why there's a huge gap between n to the k over 2 and order n, which is the information theoretic truth. So that seems to be a big sort of information computation gap here. And people believe that maybe it is inherent, and there is some evidence towards that in a line of work which studies how well sum of squares algorithms, in which the current algorithms can be couched, how well can sum of squares algorithm solve this. And there it turns out for those, this n to the k over 2 is a barrier. And so in that extent, maybe this is the best we can do with current tools. Okay, and this is all for the random case. Now it turns out this XOR principle also extends to the semi-random setting. So really, to prove our result, our main focus is the problem I said in the first slide, which is that I have arbitrary equations with random right-hand sides. How do you strongly refute it? Okay, that's all I need to focus in the semi-random model. Okay, and before I get to the technical part, just a little bit more of context. Why semi-random? It might seem, okay, so random looks fairly natural. Why do you want to study semi-random? And again, we are not the ones who proposed this model. It's existed for a while. This already existed in early works on graph coloring algorithms in some model where the graph is somewhat adversarial, but also has some random aspects. And it was ported for constraint satisfaction problems in this another work, influential work of Feige from 2007. And his motivation, as he explicitly states in this work, and he also has a recent survey on semi-random model in this Beyond Worst Case Analysis book compendium, which came out, I think, last year. And really, the question is, really, do we need all the luxury of a completely random instance? Are our algorithms so brittle that they need everything to be random, or can they somehow work in slightly more robust models? So that's one of the motivations, is can you make your algorithms more robust so they're not that sensitive to the exact random model? And in the same work, Feige gave a weak refutation algorithm for the semi-random case of 3 sat. So where the variables can be arbitrary in every clause, just the negation patterns are random. Okay, and this used fairly sophisticated combinatorial arguments of even covers and so on. There's also some coding theory connections in work of Asaf and Verstraete, which came out around the same time. So semi-random 3 sat, we had a weak refutation. And AOW also said, okay, we seem to have completely have a good picture of the random CSP world now. can they explicitly pose the question of extending their work to the semi-random setting. Okay, so that's sort of the backdrop why we want to do a semi-random thing. And also recently, it was pointed out a connection to cryptography, in particular indistinguishability obfuscation, and certain assumptions made there were pointed out in this work of Barak and others, and where again semi-random refutation algorithm turns to breaking certain schemes. Okay, so that's the context. I loop back to our result again, just recapping where we were, and then the second half, I'll talk about what we do. So our main result really is efficient ultra-strong refutation of semi-random KXR. So the problem in the first slide, we can refute strongly, namely I can prove that you can't satisfy more than 0.51 of the equations with when the constraint is about n to the k over 2, hiding polylog factors. And this immediately gives a corollary of similar ultra-strong refutation for any CSP. This corollary is actually immediate because any predicate you can just write down in the Fourier basis, and if you refute each of the XOR things, you can refute the predicate as well. Okay, so you'll actually get ultra-strong refutation for any CSP with the same number of constraints. But the connection in Allen, yeah.
Oh, sorry. I just want to ask a quick question. Hi. So the previous slide, you mentioned the motivation for semi-random. I just wanted to ask about, so Misha Liknovich, I think, had a paper a long time ago, way before this, which I thought, maybe I probably have it wrong, but I thought that he posed this question, or posed the semi-random model. Do I have that wrong?
It's very possible. I'm not, yeah, it's very possible, Tony. I'm not that
okay.
versed with the literature. So I think if you find inaccuracies, please point it out to me. This is clearly very abridged, and it might actually be inaccurate too. So, yeah, but yeah, I think that's definitely possible. And yeah, I'll be happy to find out and correct it.
Yeah, I associate it with him, but I might have the details wrong, but I'll check it. Okay.
Yeah, thanks. Yeah, and any pointers, yeah, would be appreciated. Yeah, so. I mean, it's a fairly natural thing. It's been studied in graph partitioning and other things. So in the CSP context, I mean, some of Feige's work was explicitly highlighting it, but there might have been others.
I think to me, one of the reasons it's interesting is that it's really easy to argue when you randomize over both of, both, over everything, that almost every, equation of that type is on. So then if you can only count over the assignments.
Right, exactly. Given this is a math seminar, I can also say it's interesting also because technically it gets more challenging because you have far less randomness in your system. The techniques have to be somewhat different. Though in this work, we will see that we can actually take the old techniques and sort of redo a proof for the random case, and the right proof somehow then extends to the semi-random case. So, but it does at least cause you to inspect the random proofs again to reduce their reliance on randomness. Okay, and this is for ultra strong refutation. If you just want strong refutation where you bound the optimum by some constant away from one, then using the AOW connection, now you can do it with the number of constraints which is fewer, which is n to the t over 2, where t is this degree of uniformity. So for example, for not all equal 3 sat or not all equal general k sat, it will be 1 because the predicate is not even pairwise uniform. Okay, and one other thing maybe I'll mention is that there is another model you can have, at least for balanced predicates, which is a bit nicer because at least in the math community, maybe people don't find negations a bit clunky and so on. This model is nice. You have a balanced predicate. So P for it can be majority, for example. So at least half the variables are true. And you can simply randomize the right-hand side, just like what we did in the XOR case. So you don't need these random negations and so on. And this is, of course, equivalent for the XOR case because you can shove all the negations to the right-hand side by XORing them. But what we are doing will also work in this model, which I call sort of the Goldreich model, because this is the model of relevance in cryptography, where somehow they don't want to negate everything. So it will also work in that semi-random model. So truly just random right-hand sides. Okay, so with that, I'll just sort of really the rest of the talk, you can forget about general CSPs and everything. We're just going to talk about k-variable linear equations. Okay, so that took a while, but the other parts will hopefully be quicker. But we gave a bit of context. Any questions on the context? Okay, so now we'll talk about KXR refutation. And as I said, the even case is actually quite simple. and was already known. So that's easy. The odd case is the more tricky one, and this was already manifested itself in the purely random case, as studied by Bharat Moitra and AOW. Sorry, this should be AOW. That they had to work much harder for the odd KXOR case. In particular, 3XOR is a challenging problem. So what we do is that we give an algorithm for KXOR for the, and I should say even K case is easy both in the random and the semi-random case, as I'm going to show you shortly. So we really had to focus mainly in the odd case, and we sort of give another simpler proof in the random case, and that proof is somehow the stepping stone for our semi-random work as well. Okay, so why is even K easy? So let's take the smallest even number, 2. So the ideas are already will already be clear in the 2XOR case. So you have 2 variable linear equations. Let's think of the variables as taking +1, -1 values. So each linear equation now is of the form, the product of 2 variables is equal to either +1 or -1. Okay, so you have a collection of equations of this form. xi1, xi2 is Ri, and we want to find if there's assignment which satisfies them, or prove that any assignment will satisfy only half the constraints. Okay, so we can write down an indicator for the ith variable being satisfied, which is just this 1 plus Ri xi1 xi2 by 2. Okay, so we do that, and therefore the fraction of constraint, optimum fraction of satisfied equations is exactly 1 plus the bias by 2. Just summing up over all equations, where the bias is basically just this quadratic form, summation Ri xi1 xi2 summed up over all constraint, and you normalize by the number of constraints. And this is also why a half is sort of trivial, because you get this half. If you just pick these variables randomly, the bias in expectation will vanish, so you'll get half. All right. So okay, we have a quadratic form. So let's just write it in terms of its matrix. So let's define a matrix, an n by n matrix, whose pqth entry is going to be the right-hand side of the equation if p and q together occurred in an equation. Okay. And I'm going to assume that each pair and each tuple will be in exactly one equation for simplicity. This can be handled. So, and of course, I divide by 2 because I want to make this matrix symmetric, maybe. So I have this by 2, and if they are not together in a constraint, I put 0. So just by construction, the bias is simply the value of this quadratic form optimized over the hypercube. So the largest value it can take on the hypercube, and that's exactly what I have. And now I can just say that, well, x is a vector of norm square root n if it's in the hypercube. So I simply say this quadratic form is at most n times the spectral norm of A. So the bias, which I want to prove is tiny, like at most epsilon or at most 0.1, is at most n over n times the spectral norm of A. Okay, and now you can sort of see the connections to random matrix and so on. So if so this is just reproducing what's on the previous slide. So our game is to understand bound this. Now for a random instance, is there a question?
Yeah, I'm just pointing out somehow your use of the matrix A changed. In the beginning, it was the fixed matrix describing the equations, but now it's a random matrix describing the right-hand side.
Correct. Yeah. Sorry. Yeah. So let's forget that previous A. Let's keep this one to be A. Yeah. So yeah. Thanks, Avi. Yeah. This is just the quadratic form matrix, which is different from the AX equals R matrix stipulating the equations. Now for a random matrix, if everything was random, and this goes back to what Tony was commenting, if everything is random, you have more tools at your disposal. So in particular, this is basically a sparse random matrix which has m non-zero entries. Each entry is plus or minus 1 equally likely, or maybe plus or minus half, it doesn't matter. And we want to know its spectral norm. Known bounds from random matrix theory tell us that the spectrum of this is at most square root m over n. And if m was n square, if it's a dense matrix, the spectral norm is square root n for a random Rademacher matrix. And if m is smaller, it just scales down that way, square root m over n. And that's it. So using this, if you want to certify that the bias is small, well, you just write down this matrix, compute its spectral norm, and that's a valid upper bound always. N over m times that is a valid upper bound. And with high probability, if m is, say, n over epsilon square, this will be at most epsilon. Okay, so there might be some polylog factors here I'm hiding, but that's it. And that's it. That's the full refutation algorithm for 2XOR. Just compute this matrix, compute its spectral norm, and that's a valid upper bound. And with high probability, that upper bound will be pretty small. Okay, so pretty easy. This is in the random case because now this matrix A was a random sparse matrix. Okay, what about the semi-random case? So here we will actually use a semi-definite programming based upper bound. So you have this bias, and now I will write down a semi-definite relaxation of the bias. So let's just take this M to the other side. It's annoying. So I just want to optimize the quadratic form over the hypercube. Well, how can I relax that? I can write a natural semi-definite program where I basically relax these xi's to vectors, and I write the program. You can also write it compactly this way. I optimize over PSD matrices with diagonal one entries, and I optimize trace of AX. And this is a valid relaxation because you can take X to be the outer product of any solution here, and that will have diagonal entries 1 and its PSD, and trace of AX is exactly the value of the quadratic form. Okay, so this is great. So, and the point is the semi-definite, this value can be optimized efficiently. So I have an efficiently computable valid upper bound on the bias, which I want to show to be small. Now, the main thing we need to argue is that I have relaxed this problem. So we need to argue that the semi-definite programming value is not much larger than the bias. Okay, and it turns out that is the case by this famous Grothendieck inequality, which for a general matrix here says that when I optimize over all PSD matrices, the optimum can go up, but it can go up by at most a log n factor. Okay, over what it can happen over the hypercube. So this is a well-known connection between SDPs and optimization over the hypercube. And then we are done. So basically, we know that this quantity, the true optimum, is small with high probability, and we are going. Our upper bound is only going to be a log n verse. So I've just written that down here. So if m is sufficiently bigger than n, okay, you do need some log factors here. If m is like say n log n by epsilon square, then this quantity will be quite small and it can eat up this log n factor. Okay, so again, it's the same thing. And now I didn't need to do, I didn't really need anything about the matrix A. The only thing I needed was this, its optimum on the hypercube was small, for which it was enough if my entries of A are random, not the support of A. The support of A can be arbitrary as long as each non-zero entry is plus minus one randomly. This would be the case. Okay. I mean, also we know this from where the problem comes from. We know the optimum is small with high probability, so that's it. And of course, if this log n bothers you, and you might also remember the Grothendieck inequality and the Grothendieck constant, so which is supposed to be a constant, it's not supposed to be log n. And indeed, that is the case if you allow not a quadratic form, but a bilinear form. So if I optimize over x and y, which are in the hypercube of x transpose ay, then you can also relax that as an SDP, and you can compute a constant factor approximation to that. And allowing a bilinear form will also not increase the optimum. So using this, you can actually not pay this log n price, and you get a clean refutation for 2 XOR as soon as m is say n over epsilon square times some constant. Okay, so the 2 XOR case is completely done, even in the semi-random case, even with just a linear number of constraints. Okay, and now this basically almost takes care of the even k case immediately, because if you have k is 2 times t, then you can view a 2t XOR instance as a 2 XOR instance on n to the t variables. And how do you do it? Is just the obvious thing you would try is take each tuple of variables. For each tuple of variables, originally you make a new, basically it's a linearization trick. You make a new variable y sub t, which supposedly should take the value, which is a product of these, but you're not going to insist on that. And whenever you have a constraint that product of k things is equal to ri, you just break it up into two tuples, first half and second half arbitrarily, and simply say that the product of ys yt equals ri. And that's it. And once again, if you have enough constraints like n to the k over 2 constraints and the right hand sides are random, this won't be satisfiable even in the y space. And that of course means it's not satisfiable in the x space as well. But now in the y space, you have a 2 XOR problem. The only thing which has changed is that n has become n to the k over 2. And you just apply what I said in the previous slide, and you get ultra strong refutation when m is basically n to the k over 2 by epsilon squared. So the even case is easily handled this way. Okay. Okay, so now comes the odd case, which is the harder one, and you can see why it didn't quite work out, because you can't break it up into two equal parts. Okay, so so if you just do it naively, you will get n to the ceiling of k over 2. In particular, for 3 XOR, you will need n square constraints, not n to the 3 halves. Okay, and we will just focus on 3 XOR, which is enough for all the ideas. And I'll start by discussing the random case, where we follow previous work, but in the end give a slightly, we give a different and simpler spectral analysis, which is more amenable to extension for the semi-random case. Okay, so the approach is going to be as follows. See, once again, like even K XOR. So what we'll do is we'll take 3 XOR and we will we will write a proxy 4 XOR instance, which kind of captures its optimum. And this will be using some nice Cauchy-Schwarz trick. And then we will bound the 4 XOR using spectral norm of some matrix. And the third step is the analysis step is we'll say that, well, that matrix indeed has small spectral norm. And the algorithmic part is immediate once again, because this matrix will be written down. So you just have to write down this matrix and compute its spectral. So, okay, now the first two steps are really the same as in this Barak, Moitra, Allen, O'Donnell, Whitmer work, which in turn resemble strongly what was done by Koja, Gulen, Gert, and Lanka earlier for 3-SAT and 4-SAT. But these works use a rather delicate trace argument for the last step to bound the spectral norm. And here we depart and we use a simpler matrix Bernstein inequality. And this uses somehow much less randomness, and it paves the way for the extension to the semi-random case. Okay, so let's do this. How do you turn 3 XOR into 4 XOR? So what we will do is we have these constraints involving triples of variables. X1, X3, X5 is 1 and constraints of that form. So we're going to partition these constraints arbitrarily into n groups. And now where all the constraints in group L will include XL. Okay, so, and I can do this partition in an arbitrary way. So in particular, if I take the overall bias attained by a particular assignment X and I scale it up by M, so I don't carry this normalizing factor, what is that? Well, it's basically the summation of overall equations of Xi, Xj, Xl of Bijl. Remember, this Bijl used to be Rijl, I apologize. So this is the random sign, and this is the constraint. So this is +1 if the constraint is satisfied, -1 if it's violated. So when I sum it up, I get the bias, how much advantage I get over all equations. Now I split it up over all L, which runs from 1 through n, and for each, I only sum up over constraints in that group. So all the inner things will have X sub L, so I can pull it out. So I can pull out this XL, and now inside, I get a quadratic form. Okay, and so now we can imagine just applying bounds on this quadratic form, but this is not good because there are signs outside. So we like to make everything positive. So we do a Cauchy-Schwarz trick, and again, this was done in the previous works of Barak, Moitra, and AOW. So you do a Cauchy-Schwarz trick applied over L. So this is just square root n times square root of the summation. Just this, you sum up this, take this quadratic form and square. Okay, and okay, and we just now we forget about this root n. So now this we have this inner thing, and we just sum it up over, we sum up over all L, and for all pairs of distinct constraints of what you just get by writing it out: xi, xi prime, xi xj, xi prime, xi j prime, and this big thing. Okay, so just a lot of symbols, but nothing is really going on. And of course, I dropped the terms where c equals c prime here, because that will be a lower order term. So it's that's not important. And now this is where the 4 XOR instance is coming. So basically what is happening here is some sort of resolution of something. So if you have xi, xj, xl is b, and xi prime, xj prime, xl is b prime, I sort of resolve these 2 XOR equations. I get a 4 XOR equations, where xl drops out. Okay, so essentially this is like a 4 XOR equation. Okay, but it's not a completely random 4 XOR equation, because it kind of comes, but it's sort of, it got enough pseudo randomness to argue about. So this is the bound you should have. And again, this picture is good to have. So you have XL participating in 2 triples, and I remove it, and I later call this a butterfly, because the number of such configurations is going to be important. Okay. Okay, so now the goal becomes certifying an upper bound on this 4 XOR instance. And again, what I like for the reason we like 4 XOR is that it's an even number. So I can now write this as some sort of a matrix quadratic form. So again, I can index the matrix rows by II prime and the columns by JJ prime. So this is now an n square by n square matrix. And now it's that entry will exactly be summing up over all L exactly this quantity Bijl, Bi prime, J prime L. Okay, so this sums up over all groups containing both of these. And again, just syntactically, all we need to upper bound is the largest over the hypercube of this quadratic form evaluated over rank 1 vectors like this X tensor square. But then we will actually forget about all that, and we will simply say this is an n square dimensional vector, and we will even forget that it's in the hypercube. Sorry, this should be y belongs to this. So once again, we will just say bound the spectral norm of this M and we are good. Okay, so really we're forgetting all Booleanity, everything in this problem. So it suffices to analyze the spectral norm of M and prove it is small. And this is exactly what was done in prior works using the trace method. Okay, but now we're going to inspect this last step alone in a new light. So we're now going to say that this M matrix was just a summation over all groups of some quantity. So we'll now make a matrix for each group. Right, so for each L, we make a matrix AL, which is again n square by n square, and it simply tells, is there, for a particular pair I prime J prime, it simply tells, does that butterfly which I showed exist? Is IJL and I prime J prime L or both constraints? If so, it puts the product of those right-hand sides. Otherwise, it puts a 0. Now, the thing to note is that these matrices are random, and the way I've defined it, they're symmetric matrices, random. Their mean is 0 because these are random independent signs for different constraints. And they're also independent across L because these constraints are completely independent. I mean, the right-hand sides of the constraints are independent. Again, just jumping ahead, it'll turn out this independence continues to hold even in the semi-random case, and that's going to be our foothold to just make things go through. So now we want to bound the spectral norm of this M, and it's a sum of independent mean 0 matrices. So there are various forms of matrix Bernstein inequality. This is the one we'll use, is that the chance that the spectral norm is large, like at least T, falls off sort of like a Gaussian in T with the scaling factor, which depends essentially on how big is the spectral norm of each of these A sub L, and also what's the total variance of these matrices. So these are all symmetric matrices. So instead of AL transpose, I'll just have AL square. So I basically sum up AL square over all matrices and take its expectation. Okay, that's the variance term. So this is just in the one-dimensional case, this is exactly just the standard Bernstein inequality. And here it's the matrix Bernstein inequality, which bounds the spectral norm of as long as you add random independent matrices, each of which doesn't have big spectral norm and their total variance is small, then I get a pretty good concentration on the spectrum. Okay, so now we finally have to bring in specifics of the problem. So far it's pretty generic. We just stare at these matrices, and we can definitely apply this matrix Bernstein inequality. They are mean 0 random independent matrices, but we just need to handle on what's their spectral norm and their variance. So it turns out the spectral norm is very easy because you don't have too many constraints, and these constraints are random. So just by throwing out some constraints or by just giving up little lower order terms in our upper bound, we can effectively assume that each pair of constraints is in exactly one constraint, one triple. Okay, so because of this, if I look at a particular row I prime, for a particular L, there will be a unique J at most for which IJL is a constraint, and there can be a unique J prime for which I prime J prime L is a constraint. So there will be, in the I prime throw, there will be exactly or at most one non-zero entry. So this matrix is going to be extremely sparse and simple. Each row will have at most one non-zero entry, and that entry will be random plus 1 minus 1. So because of this, just using the, each row is at most one non-zero entry of magnitude at most 1, the row sum is at most 1, so the spectral norm is at most 1. So the spectral norms is really not a problem. It is just at most 1. Okay, I've just written down the same thing from last slide. This is the matrix. Now, the other term we need to worry about is this variance term. And again, what I just said in the previous slide in slightly different notation is that if I count the number of constraints involving xi and xl, let's call, inside group GL, let's call that degree sub L of I. And what I just said in the previous slide is you can assume these degrees are basically 0 or 1. And that's what tells you that the spectral norm of each AL is at most 1. And further, because of this, you can also argue that if I take the variance matrix, the summation of AL square, that will also actually happen to be a diagonal matrix, because every pair of rows in AL are going to be orthogonal, because each row and each column has at most 1, 1. So it will be a diagonal matrix. And what will that entry in I prime be? It will basically be the number of common L, or number of L in which both I and I prime participate in a constraint. So this sort of cross product of degrees. Okay, each of these is like 0 or 1, but I have to sum it up over all L. And again, this best way to think about it is this picture, which is that if an I and I prime have a J and J prime for which this configuration occurs, then I count 1. And I just need to find the number of groups where such butterflies occur. Okay, so this is what I just call the butterfly degree, sort of a mnemonic. And so we just need what's the butterfly degree. And for a completely random instance with n to the 3/2 constraints, a simple calculation will show that all the butterfly degrees will be at most log n with high probability. Okay, because if I take a particular pair, you can say that the expected number of butterflies that will be there and is at most will be a constant. And so if I give a log n deviation, I can ensure this for all pairs of variables. So all the butterfly degrees will be at most log n, and that's the spectral norm of this matrix is actually therefore the variance term is also at most log n. Okay. And in fact, these are actually deterministic statements. Even I don't even need really the expectation here, because I'm just talking about the support size. So the butterfly degree is at most log n, and I just plug in sigma square is log n here. As long as t is about log n, my spectral bound will be valid with high probability, and that's what I get. So spectral norm is at most log n. So looping back to a few slides, what we really had by the Cauchy-Schwarz was we had a square root n, and then we had this optimum over the hypercube, which we said was at most n square m. Okay, again under square root because of Cauchy-Schwarz. So if you know the spectral norm of m is at most log n, we basically say that the bias is at most epsilon, which gives you ultra strong refutation as soon as m is about n to the 3/2, give some polylog factor slack. Okay, so that's the random 3x. Okay, so in the last few minutes, I guess I have 5 minutes. I'll try to say what we do.
No problem. Yeah, 5 or 10 minutes. It's good.
Okay, good. Yeah, I think, yeah, that sounds, I don't have too much more to say. Really, this is pretty much what I said so far is all things were known. The new part here was this matrix Bernstein-based analysis of random 3XR, which is a lot cleaner. And really, this is pretty much the entire analysis I showed you, modulo just checking, trusting the facts I said about these variance term and other things. So it's pretty clean. And then it turns out, therefore, this doesn't use that much about the random instance, and we can actually make it work for the semi-random thing with a bit more work. Okay, so that's the last part I'll say something about. So now extending to the semi-random case, so we have these matrices, some of these matrices A sub L. Now, the entries of this matrix are still random because these signs are random and independent across constraints. And the matrices are also independent because the matrix for L and the matrix for L prime, the signs are still independent. So while the support structure of each AL can be adversarial, the entries are random and definitely are also independent across different groups. So you do have some of independent mean zero matrices. So you can apply the matrix Bernstein again. I mean, the trouble is these variance term can be large, and in even the spectral norm of even a particular pair IL can occur in lots of constraints. So even the spectral norm of one of these A sub L can be very large because there can be a row which is filled with a lot of ones or non-zero entries. So you can't just use a simple row sum upper bound.
Venkat,
So
yeah, a question.
Yeah, sorry. Yeah.
Suppose an equation repeats itself many times. How do you, what do you do about it?
Yeah, so I'm hiding that in this talk, but really instead of BIJL, you should just sum up the right-hand sides over all those repetitions, and then things will work out.
Okay.
Yeah. But we do allow that too. So yeah, so the two issues which can happen is that the degree itself can be large. I can participate in a lot of constraints in group GL, and then the butterfly degrees can also be large. There can be lots of groups which contain both I and I prime. The first issue is can be handled relatively compactly by basically if you have a large degrees, you just peel off a separate instance where those large degrees occur, and then that basically gives you a 2 XOR instance. Again, I'm hiding the details here, but it's not difficult. You can refute it as a separate semirandom 2 XOR instance using the semi-definite program. So if lots of constraints involve a particular pair of variables, then it becomes easy. And intuitively, the reason is that if xi, xl occur together in a lot of things, you can really pretend a new variable for that product, xi, xl, which can only take one value. So then it participates together as one variable, and the other variable makes it a 2 XOR constraint. So if you have lots of this, then you effectively get a big enough 2 XOR instance, which is semi-random, which you can refute, and you'll be done. Okay, the second issue requires a more refined analysis, basically because you have to deal with different scales of this butterfly degree separately and bound their contributions. Okay, so I'll be somewhat high level and vague here, but just give you the gist of how it's done. So again, recall the matrix we had before, which was summing up for I prime, J prime, all the groups of these equations. So we now change this matrix slightly by normalizing it by the size of the group. So in a completely random instance, all these groups have roughly the same size. So this was not present, but now different groups might have different sizes because XL might participate in lots of constraints. So we scale this down. Effectively, this is the right scaling for which Cauchy-Schwarz gives you the most bang for the buck. So it's a bit technical, but it turns out this is the correct choice to make. So using the correct Cauchy-Schwarz, basically it just turns out this is the matrix whose quadratic form we need to upper bound. Again, it's not important what this quantity is. I just wrote it down for precision. So this is the same quantity we had before. Now the matrix is slightly different. And now we will do, earlier we simply said that we bounded this using the spectral norm of M. Okay, and turns out now we cannot quite do that. So instead we'll use a relaxation saying that, well, we'll forget that these vectors are tensors. We will say it's at +1, -1 vectors, but we'll say this is at most the bilinear form over the hypercube. Okay, Y transpose MZ. And this quantity is called the cut norm of M. Well, in the +1, -1 world. Okay, so this is a well-studied norm. So this is what we will try to bound. Okay, so again, we're going to use Booleanity of these things in some limited way. And again, earlier we simply used that this cut norm was at most n squared times the spectral norm, but now the spectral norm may not be small, so we cannot quite go that route. And again, we'll have these butterfly degrees to contend with, which is basically the number of such configurations xi and xi prime participate in group L. And you hear the right thing to do again is to scale it down by the size of the group. Okay, so that's what we use, which is correlated with this definition of M. Okay, and then this is basically the last technical slide. So we have this butterfly degree. Now, it's true that some of these butterfly degrees can be large, but the total number of constraints you have is only M. So by counting this up and using a simple Cauchy-Schwarz, the total butterfly degree cannot be too large. So what this then says is that you can take these pairs I prime and just group them into logarithmically many intervals based on what this value bi prime is, and basically break up this matrix M into associated blocks. So you have this big matrix n square by n square. Each row belongs to some BP, and each column belongs to some BQ. So you just break it up into those sub matrices which are disjoint, which is just projects M onto those rows and columns. And we just use a simple triangle inequality, saying that the infinity to 1 norm of this is at most the sum of these infinity to 1 norms. And now for a particular P and Q, because all the butterfly degrees are similar, we just move to the spectral norm. Okay, and we just use the fact that that matrix has small support. It's only supported on BP and BQ. So we can just play this factor for Boolean vectors. So we sort of use Booleanity in the sense that if I take a Boolean vector and project it into a small number of coordinates, its L2 norm on those coordinates is going to be square root of that number. Okay, so it doesn't have very large entries. And that's what we do. And now it turns out that each of these is good enough to bound by matrix, the earlier matrix Bernstein thing. It's true that the bound might sometimes be large if the butterfly degrees, if this P and Q are large. But then by this overall weighting thing, the BP, BQ will be correspondingly smaller. So it's just a delicate balancing act and the overall bound works out. Okay, so, and we lose some polylog factors here because we are a bit sloppy in, we're breaking up P and Q are range over a log n size each. So we lose some log square factors here. Okay, so that's all I had. So the main result was just for KXR with random right-hand side equations, we can refute it strongly as soon as you have n to the k over 2 times polylog factors. And this is based on spectral methods, but some part of it had to account for Booleanity because we don't have complete randomness. And then using completely known earlier reductions, this gives the state of the art for CSP refutation in the semi-random model, matching what was known for the completely random model in terms of number of constraints. Okay, so that's the main.
Is that except for the polylog factors?
Except for the polylog factors, again, yes. Okay. And it turns out polylog factors can bite you, so I'll come to that. And so there are many open questions, so I'll just highlight a few of them. The first immediate one, which really should be doable, we haven't done it, is to extend it to non-Boolean domains. Again, this was done in the AOW work, and we just haven't, so this is still not done yet, but it should be, I don't expect surprises there, I suppose. Another interesting question is to extend it to this smoothed model. So in this model, in this work of Feige, which I mentioned for the semi-random CSP thing, the actual model he works with is actually a bit more general. He take an arbitrary 3-sat instance, and now in every class, every variable or every literal, you flip it with probability epsilon. If I take epsilon to be half, I get the semi-random model, but epsilon can be much smaller. And his algorithms work in this model too. And it's an interesting question whether our algorithms can be extended to this model. So I think it's a very nice question. And this gets kind of moves the needle even closer to worst case than semi-random. So it's definitely very interesting. And this Feige Kim effect paper is amazing. It's one of these, it's sort of an island. It's one of these things where you actually have a non-efficient refutation, which beats what we can do efficiently. So this gives a non-deterministic refutation. It proves that, so there is a short proof of unsatisfiability even when there are only n to the 1.4 clauses for 3-sat. And later, Whitmer in his thesis extended it to k-sat and the bounds naturally extend. But doing this for other things and strong refutation, etc., is wide open. So as far as I know, there's not been any follow-up on this, and there really should be, because it's a very nice direction where inefficient refutations are doing better than efficient ones. And the last thing I'll mention, which where the polylog factors bites us, is you can say, okay, what happens when you go below n to the k over 2 equations? For example, when you go to n to the 0.9 times k over 2 equations. So this has been extremely well studied in the random XOR case. Okay, let's just focus on XOR. And this was done in this paper of Raghavendra, Rao, and Schramm, which gave algorithms using the sum of squares and using spectral methods, but you can also think of it as sum of squares upper bounds. And this has been matched in this work of Kothari, Mori, O'Donnell, Whitmer, showing really tight 3-way trade-offs. And this gives you basically roughly this many equations, you can refute it in 2 to the n to the delta time. So this kind of smoothly interpolates between polynomial time at n to the k over 2 and exponential time at n, right? Maybe there should be a +1 here. There's something wrong, but you get the idea between n to the k over 2 and n. And there is also a simpler argument to RRS using this Kikuchi hierarchy, which was done by Alex Wayne and in personal communication, which works only for the even k case. And we believe this work with some losses extends also to the semi-random model. But here the polylog factors sort of hurt us, because instead of getting this n to the 1 minus delta, maybe there'll be a constant factor in front of that, because basically polylog of like 2 to the n to the delta now becomes like n to the delta. So the polylog factors sort of hurt us a little bit here. So it'll be nice to avoid some of these in our main algorithm and then try to extend it in the sub-exponential regime. Okay, so I think that's all I have, and we'll stop here.
Thank you. All right, questions to Venkat?
I have one. What else is new? Actually, I have two. So one, I never heard of the Kikuchi hierarchy, so I'd like to know what that is. But my other question is, this seems similar, this phenomena where you get a good bound for 2, but then to get it, so then you can get it for the even ones using this trick, but doesn't work for the odd ones. Like it comes up also, like I think if you want to estimate k-way marginals privately, I was wondering if you thought about that and whether these, this is a really cool technique that you have. I just wondering if it.
So the second question, I haven't, I don't know this k-way marginal private thing. It sounds, I would love to hear more about it. So I guess you should, along with the reference of Aleknovich, you should tell me this. And for the Kikuchi thing, actually, I'm not too familiar, but I can tell you what the matrix they sort of work with is that they take a big matrix where they have big tuples, L tuples of variables, where L is going to be like n to the delta on the rows and columns. And if the symmetric difference of those tuples is of, let's say k is 4, so it's a 4 equation, then they put that right hand side. But most of the matrix they leave to be zeros. So as opposed to sort of putting all the information you can on those on that entry, you only put the sign if they all XOR to an equation which is in the scope of it instance. So it's a very sparse, very crisp matrix. And so this was done in some another paper with also Chris Moore and Alex Wayne and others in a different context. And I think the Kikuchi hierarchy was used there. And so this is just another application of that.
It's a hierarchy in what sense? Is it like the same?
Oh, it's a hierarchy in the sense that you can still increase L, the size of the row number of, the rows and columns are L tuples, and you can scale up L. So you basically use L to be n to the delta. And so you get sub-exponential refutations, and the clause density falls down as roughly what I wrote.
Cool. Okay, thanks.
Except for the fact that when delta is 1, I'm writing 1 equation that shouldn't be there. So it should probably be a +1 somewhere there. So,
do you have any good understanding of where the Feige-Kimofek bypasses the sum of squares lower bound of n to the 3/2? Like, what kind of proof system is it that allows it to get n to the 1.4?
It's a good question. I sort of don't have their work fresh in my head. So, but they do certain things of finding like short linear combinations. So there is some connection to these even cover problem and stuff. Maybe someone else in the audience knows this work better and can comment on it. But it's some sort of ineffective argument saying that if you have enough of these, there must be some short linear combination which gives you a contradiction, and they use those to build the proof. But finding such short linear combinations seems hard, and in particular, it's not the kind of thing SOS does well.
Just a comment, I also don't remember the details, but there's a work of Müller and Zamella to show that this proof can be carried out in TC0 Frege.
Yeah. Isn't it a lot of stuff about formalizing expansion type?
Yeah, that's the hard stuff. The easy stuff is this, there are these parity constraints where something is odd and you gain something. This is like this combinatorial structure that you can prove exists, but it's apparently hard to find.
Okay, do you have any reason to believe that something like this should not be doable in for efficient algorithm, Venkat?
For me, it's intriguing because there is a gap. So it's quite possible that, of course, if you match it with efficient algorithms, it'll be interesting in one sense, but sort of also boring in another because there won't be this discrepancy.
Well, but there'll be a new algorithmic technique.
Boring. No, true. Like I don't know. My sense is people have tried, and it seems like it's one of those things where this pigeonhole or combinatorial argument shows the existence of something and people don't know how to constructivize it. But you're right. I mean, doing it will definitely be very interesting and give a new tool.
Yeah, similarly, I mean, there is no reason to believe that 1.4 is the right answer. Maybe there is a linear upper.
Right, exactly. Can you go further would also be interesting, and also generalizing it to some other CSPs would also be interesting, and so on.
More questions to Venkat? Anybody?
Yeah, regarding the higher alphabet, does AOW actually tell us completely what happens in random label cover instances?
Oh, random label cover. It's a good question. I think, I mean, looking at their statements, there don't seem to be any qualifiers. So, but maybe what is hidden under the hood is this assumption of T uniformity, etc. Maybe that just becomes pretty bad in the label cover thing. But
yeah, because I mean, I remember there was also a paper of Pasin and Dana Moshkowitz, etc., Arvindan, etc. And I think they were studying random label cover there, and it seemed like people didn't know what the right answer is. There were still some gaps abounding.
But maybe they were really thinking of label cover where the alphabet was growing with n, or was it still fixed?
Oh, alphabet was growing there, yeah.
Yeah, so no, that would be a different soup altogether. But I think in this AOW, you fix Q and K and let n go to infinity. Maybe they nail it completely. Yeah, that was my sense from their statements. Yeah.
Okay. Yeah. Okay. Yeah. That probably answers the question. Yeah.
And at least from their, the details are in an appendix, and from what it doesn't seem like there's any surprise there other than executing the Fourier analysis in this higher domain. So.
And it's a question of getting it's completely non-random. So you started with random, moved to semi-random, but having an explicit hard right-hand side is basically a de-randomization question, or can be viewed as a. So is it known even in the something like this, even in the k equals 2 case, in the cases where we have how to choose a hard right-hand side? Do you have any? I mean, in many of the random arguments for lots of this type of results, the argument relies on some randomness, but sometimes you look at it and you say, that's a pseudo-random property that can replace randomness, and it's done in various, I don't know, 40s, or maybe here it's done something like this for random colorings of graphs, and but anyway, is there
that's a great question.
You use the Bernstein inequality, matrix Bernstein, but maybe you can fool it with some.
Yeah. So there's a related thing where this comes up. I think I've not sort of seen it so much in the CSP world, but you can ask, I give you a span of A, I mean, I give you a fixed thing, which you can think of as a code, and then asking for a right-hand side, which is basically asking for a point which is far away from the code.
Right.
And doing this explicitly is, not known, and it has connections to matrix rigidity and stuff. So I think in that spin, people have looked at this. How do you find a right-hand side, which is guaranteed to be far from the span of the left-hand side?
But here you can pick both A and the right-hand side. The question you are talking about.
Okay. So then.
But here you can.
Yeah, then I think maybe, except for the fact that these rows being sparse is not something which is common in coding theory, probably it becomes just a question of finding a code and a point which is like a deep hole for it or something, which is very far from the code. I think that we can do for, say, for example, for Reed-Solomon code or something, but it will be a very different regime of parameters. So.
Okay. Yeah.
So there's also some work which uses high-dimensional expanders to do this in the context of sum of squares lower bounds.
Right. Yeah, there was this recent paper which gave explicit sum of squares lower bounds for 3XR and stuff up to. It doesn't match what's known. It doesn't get linear levels. It maybe gets log levels or something. But yeah, I saw that.
Yeah, that's your paper, right, Yuval? I think.
Yeah. More questions. All right. Okay. Thanks, Venkat.
Yeah. Thanks, Avi, and thanks to all for the attending and the questions.